This is the first video in a two-part video series discussing polar coordinates and calculus. In other words, how can we compute the area inside of a polar graph or to find the arc length of a polar graph? This requires calculus, of course, as we've seen before. In order to do this, we'll have to convert some of our formulas from their rectangular coordinate system form into a polar coordinate system form. Remember that when we are on a rectangular coordinate system, the definite integral, of which you see an example here, gives the area between the curve and the x-axis, with the area above the x-axis being positive and the area below the x-axis being negative. Look at the picture here produced in Desmos. The purple area is above the x-axis and between the x-axis and the curve, so it carries positive area. The area below the x-axis and the curve is gray, which represents a negative area. The net area is represented by the definite integral. In order to compute a definite integral, we used a Riemann sum. To find the exact value, we took the limit of the Riemann sum. We'll need to do something similar, but we cannot use rectangles since that was only effective on a rectangular graphing system. Our graphing system is based on circles, and as you might expect, we're going to use something related to circles for the Riemann sum here. In this picture, you'll see in this dark color a curve which is extending from just inside the fourth quadrant around through the first quadrant, ending somewhere in the second quadrant. In order to approximate this using a Riemann sum, we need a shape that will fit onto a polar graphing system. The polar graphing system, as you see in the background, is based on concentric circles. So it makes sense to carve this out into what are known as sectors. They're sort of wedge-shaped pieces that extend from the pole out to where it touches the axis, and then with a line coming across that would create essentially a triangular bottom. In fact, the true wedge does not have a triangular bottom. The true wedge, if we're looking at it, looks like the following. The true wedge is going to come out from the pole with a corner and have some kind of curved end on the end of it. It's not really the sector of a circle because this part where the curvature is probably not on a circle itself. It is, however, curved, which makes the circle a reasonable approximation to it. Let's take a look at how we can develop this formula. Realize that in this figure, what they are trying to compute is the area that is between the angle theta equal to A up to theta equal B, or, as we typically use for angle measures, alpha and beta. Let me shade in the region here so that you can see the area we're trying to find. You can see now in the picture that in the pink shaded region, I do have what looks like sort of a sector of a circle. We do need to divide it up, however, into smaller partitions, just as we divided graphs on a rectangular system into different rectangles. The more wedges we use, the more sectors, the closer the approximation will be to the true area. We can find the number that we are going to use and represent it with n, just as we did for a Riemann sum. In a Riemann sum, we computed the width or length of each rectangle by taking b minus a and dividing by the number of rectangles. We do the same thing here, only in this case, because it is an angle and no longer x, we are subtracting alpha from beta and dividing by n. That will give us the change in the angle of each of these sectors. Realize that each sector has a different change in angle. What we'll do is allow the widest one of these sectors to go towards 0, meaning that we take more and more sectors or wedges until n goes to infinity. When that happens and we take that limit, we should be able to find the precise value of the area that is here in pink. Now the area of a sector on a circle is 1/2 r squared theta. Your book gives you one definition for it, but I want to give you a different definition for it, which will help us to understand how the wedge is being used as an approximation for this area. One of the formulas that we have from geometry when we studied circles is that arc length is given by r theta. Remember that arc length is the length that the piece of pizza has along the crust. In other words, if you grab a piece of pizza, how long is the crust? It's not flat, it is curved because the pizza is a circle. This becomes r theta. That means that we can solve for theta by dividing both sides by r from this equation here. Then we let the number of partitions or the number of wedges or sectors go to infinity. If we increase the number of wedges, let's look back at the previous picture. If I'm not changing the pink shaded area, but I use more and more wedges, then each wedge's change in angle must get smaller and smaller. In fact, as n goes to infinity, we will allow delta theta to go to 0. Again, if you're in a real analysis class, you would discover that you could name the widest one as the mesh, and the requirement is that the mesh itself must go to 0. Otherwise, you cannot use this sum to approximate. Provided that's true, as the sectors become narrower and narrower, the curvature of the arc becomes less and less. As it's becoming less and less, it becomes flatter and flatter, which means that we could approximate the area of the sector with the area of a triangle. The area of a triangle, of course, is 1/2 the base times the height. Let's draw that on our picture here. On the picture, I'm going to draw a triangle that connects the two corners where the crust of the pizza would be with a straight line. Now, you'll have to forgive me because my hand's not all that steady. This forms a triangle. Again, we're cutting off sort of the edge of the piece of pizza, and we're creating a triangle. I've redrawn the line connecting the two ends of the curved crust in a way to exaggerate where it is. It's actually much closer to the arc than it appears in the picture. If I look at this now, because it comes out of a circle, that means that this is essentially an isosceles triangle. However, in my picture, these sectors are not coming from a circle because the shape that I'm trying to approximate the area inside of is not a circle. That means that these ends, while curved, are not exactly the edge pieces of a circle. However, I can approximate the area if I now take and find the perpendicular distance between the flat edge here connecting the corners of the arc or the crust with the point or the vertex of the sector. Then I can use the formula 1/2 base times height to find the area of the triangle and let it be the approximate area of the entire sector. Keep in mind that when I'm approximating the base is actually what is approximated is the arc length. And we can look at our formula again from the previous page. Arc length is r theta. That means I can replace the b, the base of the triangle, with r theta. What about the height? If this were truly on a circle, then coming from the vertex here of the sector all the way to the arc, which would of course go past a little bit of the triangle, that would give me the radius of the circle. I can approximate it by letting h, the height of the triangle, be approximately r. As we allow delta theta to go to 0 and the number of sectors to go to infinity, these become equal to one another. And this leads to our formula that the area of the sector is 1/2 r squared theta. This is sort of a different way of looking at it that hopefully will give you a feeling for why the formula for the area of a sector is 1/2 r squared theta. Now we can put this information together with what we know about Riemann sums to find the area bounded by a polar curve. Remember that the area of the n shapes that are used to produce it is the area of each individual shape. For a rectangular system, each individual shape was usually a rectangle. For a polar system, it's a wedge or a sector. We'll add up all n sectors. This, however, is approximately equal to the area of that triangle, which is 1/2 delta theta times f of theta sub I. Now, where is the delta theta and the f of theta sub I coming from? Let's look back at our previous picture of the sector. Remember that the formula is here, 1/2 r squared theta. Delta theta then is the measure of this angle here inside of each individual sector. Delta theta is the change in the angle inside that tiny little wedge. What about the f of theta sub I? Well, f of theta sub I, since we are in a polar system, is r, because in a polar system, the dependent variable is the radius r, which depends upon theta. In other words, this formula, 1/2 r squared theta, is in fact the formula that you see here. Delta theta is theta, the measure of the angle inside the sector, and f of theta sub I is the measure of the radius in the ith wedge, and of course it's squared. As we take the limit as n goes to infinity and delta theta goes to 0, we can get the precise value of the area. To do this, we define it to be the definite integral of 1/2 from alpha to beta of f of theta quantity squared d theta. But f of theta is r, and that gives us 1/2 the integral from alpha to beta of r squared d theta. Here's the formula in its final form, 1/2 the integral from alpha to beta of r squared d theta. The most difficult part of finding the area inside of a polar curve is finding the correct values for alpha and beta to use in the definite integral. This is when you're going to need a graphing calculator so that you can use the option that I describe as looking like an old-fashioned key. It's represented on the graphing calculator with a dash followed by a 0. You can use Desmos to find the right points, but because Desmos is not as robust in the polar system, it can be quite tedious because you have to keep calculating different values and it will continue to give you decimals instead of exacts. The best way is to adjust the window on the graphing calculator until you can get it to graph only the part of the graph that you want that's shaded in. Let's start and look at this with the first example, which is a cardioid with the equation r equals 1 minus sine theta. Let's switch to the graphing calculator and see if we can find the right setting for the window to get only this right half of the cardioid graphed. It is easiest when you can find a range of theta values that will graph it from here around to the upper part in one fell swoop. In other words, we often will use from a negative angle around to a positive angle. Let's use the graphing calculator now. Take a moment to input the equation into your graphing calculator. Be sure that you are in polar mode and that you are also in radians. Make sure also that you move the cursor to the far left and change that dashed or dotted line into the key shape, which is also a hyphen followed by the 0. Remember that you can do that by using the cursor key to move it all the way over there to the far left. When the cursor is on top of it, it will begin to blink. If you hit enter twice, you should get the key shape. Now we need to check our window. We probably left the window from 0 to 2 pi and the theta step by pi divided by 60, since it's my favorite. Now we need to graph it, but we do need to use zoom fit, since we've certainly changed the equation from the last time I graphed something, which I believe was probably the butterfly. Let's choose zoom fit so that we can get the best XY window to graph the equation. Remember that that is choice 0, or you can scroll down till you find it. The graphing calculator will take some moments, indicated by these rotating lines up here in the corner, to find the right window. I can see that it's having rather a little bit of trouble coming up with the right equation, but it finally got it. Here it goes, drawing the cardioid. Notice where it started. It started up here in the positive x-axis, and it is graphing it in a counterclockwise direction. Notice that it is now graphing it again, meaning that when I go from 0 to 2 pi, I'm getting this thing twice, which is not what I want. I only want the right half. Let's see if it stops. Oh no, it's going again, 3 times at least. Coming around again. This will help me narrow down what I need to cut the window down by in order to get it to graph once. Notice that it is going again. Oh my goodness. Let's stop it so that we can change the window. If you hit the on-off button, it will interrupt the cycle, which is handy when you accidentally set the window way too large. Let's come back to our window and find out what would happen. Oh, I see what happened. If you look here, you'll see that in fact I wasn't going to 2 pi. I was going to, I don't know what that would be. It's a lot. 8 pi, I believe. Let's change it back to 2 pi and see what that does. Remember that pi is on the caret symbol, and it's the second function. When I hit enter or graph, it will now go. Let's go back and graph it again and make sure that this time it doesn't keep going and going. It starts again on the polar axis, which is where the positive x would be. It's graphing it in the counterclockwise direction, and it's coming back around to the polar axis, and it stops. That means from 0 to 2 pi, I get exactly what I need. Now, the problem is the area I want is only the right half. The area is not halfway through. However, if I look at the graph, I can see, if I check very carefully, that there are in fact 2 tick marks here on the graph. This indicates that the y value down here at the bottom might in fact be 2. I can find the y value if I want to by using the calculate button. I believe that that angle would represent 3 pi over 2, but that sometimes does not work. Remember that it can give you a negative r, which would shoot it out on the opposite end. Let's try second trace, which gives us calculate. It's asking me to calculate a value. I want to try the value at 3 pi divided by 2 and see if that is the one down at the bottom of the screen. So I enter 3 pi divided by 2. When I hit enter this time, I get it blinking where it is. It gives me a y value of -2. Notice that this is down here at the bottom of the screen. Notice that it gives you the r equation as well. If I were to plug in the value for 3 pi over 2 into this equation that you see here, the sign of 3 pi over 2 is -1, so the double negative would then give me a +1, and 1 plus 1 would give me 2. In other words, from the pole, it is 2 away down here at the bottom. That is the ordered pair 3 pi over 2, 2. On the xy coordinate system, It is the point 0, -2. Now I can use that value to start trying to figure out how to get it to graph only the part I want. I'm going to go back to the window, and I'm going to tell the window now not to start at 0, but instead to start at 3 pi divided by 2. When I do that, it will go only from that point around. Let's graph it and see the part of the cardioid we have now. You can see it started at the bottom, but unfortunately it stops when it gets to the axis. This is not exactly what I want. I need it to come back around to the pole and stop. Well, remember that when I'm at the pole, the angle could be any angle at all, but the radius is going to be 0. Let's take a look again at our equation and see if we can figure out what that radius would need to be. To be at the pole, I need r to equal 0. That means that 1 minus sine of theta is also equal to 0, which means that the sine of theta equals 1. Now there are infinitely many angles whose sine is 1, but the most obvious choice would be pi divided by 2. However, if I were to tell it to go from 3 pi over 2, I cannot tell it to then go to pi over 2. That will not continue it in a smooth arc. However, there is another angle that ends me in the same place as pi over 2, but occurs after 3 pi over 2, namely 5 pi over 2. In other words, we need to add on a multiple of 2 pi. This would be pi over 2 plus 4 pi over 2, which would bring me around to 5 pi over 2. Let's go back to the graphing calculator and see if that is the correct place. On the graphing calculator, go back to the window and select now to go from 3 pi over 2, which is already in there, and instead of stopping at 2 pi, let's go to 5 pi divided by 2. Let's see if this gives us the right value that we need. Now, when I hit enter and then graph, it should graph it again, beginning at 3 pi over 2 and extending around until it reaches 5 pi over 2. Boom! That's exactly the region whose area I am trying to find. Those then will become the limits for the definite integral. Are these the only values I could use? Of course not. I could find multiples of these by 2 pi by adding 2 pi to both or subtracting 2 pi to both, or any integer multiple of 2 pi. Let's now do the calculus and find the actual area. We have discovered that the integral we need to evaluate to find that area of the shaded region is the integral from 3 pi over 2 up to 5 pi over 2 of, well, what was our formula again? Remember, it's based on the triangle 1/2 r squared theta. If we move up, you'll see again that that's exactly what we need, 1/2 r squared d theta. Now we can move the 1/2 outside of the definite integral and write it at the front. We need the radius squared, so we'll have to come back to the equation to find the radius, which is 1 minus the sine of theta. That needs to go in parentheses and squared. Then we have the differential d theta. Please remember that when you square something that has 2 terms, you must end up with at least 3 terms. This is because the outside and inside do not cancel. Don't give me 1 plus sine squared of theta. This becomes 1/2 the integral from 3 pi over 2 to 5 pi over 2 of 1 minus 2 sine theta from the product of the outside and the inside using the FOIL method plus sine squared of theta d theta. I can split this into 3 different integrals to finish evaluating. This will give me 1/2 the integral of 1 d theta, which of course is just theta, but evaluated between 3 pi over 2 and 5 pi over 2. We'll wait and plug it in at the same time. What about the integral of 1/2 times -2 sine of theta? Well, the 1/2 and the -2 would cancel, but I would be left with a -1. The integral of sine of theta, however, has an antiderivative that is negative cosine, since it is the derivative of negative cosine that would give me sine. That then would cancel the negative that I got from the constants. Again, the antiderivative of sine is negative cosine. What about the last one? This one, of course, is one that you've learned to do much earlier this semester when we were talking about trig integrals. You have sine to an even power, and you are going to have to use the double angle formula in order to rewrite sine squared in terms of cosine of 2 theta. Since sine is normally an odd function when we're talking about the xy coordinate system, this is the one that has the negative in the middle. This is going to be 1/2 of theta plus cosine of theta, both to be evaluated between 3 pi over 2 and 5 pi over 2. And now the changed integrand, which is going to go from sine squared of theta and become instead 3 pi over 2 to 5 pi over 2, 1 minus the cosine of 2 theta, all divided by 2 d theta. Remember that this is the double angle formula that you need to change an integral of sine squared into something that can be computed using basic U substitution. For the next step, what we need to think about doing then is plugging in the limits of integration to the first 2 terms, pulling the 1/2 out of the integrand, and then integrating 1 minus cosine of 2 theta. Since that's mostly calculations, you should pause the video here, do the work, then turn it back on to see whether or not you got the right answer. Your next line should include evaluating the first term at the upper and lower limits of integration, and the second term at the upper and lower limits of integration. Pull the 1/2 constant factor out of the integrand, then distribute it across the 2 integrals found by splitting up what was in the numerator into 2 different integrands. The integral of 1 d theta will be simple, but the integral of cosine 2 theta d theta will require U substitution. You'll notice that I've abbreviated writing the 3 pi over 2 and 5 pi over 2 by writing alpha and beta instead. This is okay, as it can get a little onerous to keep writing them over and over. Let's look at the next line. In the next line, we subtracted 5 pi over 2 minus 3 pi over 2. That led to 2 pi over 2, which reduces to pi. As a consequence, this first term will simply become pi over 2. The second evaluation of the upper and lower limits of integration into the second term are both going to go away, since the cosine of any multiple of pi over 2 is 0. These are now gone. Splitting up the 2 integrals from here gives me a 1/4 of theta, which needs to be evaluated between alpha and beta. Remember that alpha is 3 pi over 2 and beta is 5 pi over 2. This leads to 1/4 of 5 pi over 2 minus 3 pi over 2. We've already calculated that, though. We did it here, and we know it gives us pi. That means that this term then will become, in the next line down, plus 1/4 of pi, or we could write it instead as pi divided by 4. The last integral, we need U substitution. We allow U to be 2 theta so that du is 2 d theta. Solving for the differential d theta gives us du over 2, and we pull the 2 to the front of the integral as a constant factor. And the next line, this would give us a minus 1/8. The antiderivative to cosine is, of course, sine. This would give us the sine of u, or back substituting, we can replace u with 2 theta. Then we need to evaluate this between the values of alpha and beta. And the next line down, this means we can take the minus 1/8 out and consider only what's left. This will be the sine of 2 times the upper limit of integration, 5 pi over 2, minus the sine of 2 times the lower limit of integration, 3 pi over 2. Remember that the 2's will then cancel, of course, and this will then give us a multiple of pi in both cases. Well, it turns out that the sign of multiples of pi is, you got it, 0. That means that these parts zero out and disappear from our evaluation. This gives me pi over 2 plus pi over 4. The common denominator of 4 leads to 3 pi over 4. That is the amount of area that we have contained in the cardioid that we drew up here between the angle for 3 pi over 2 around to the angle for 5 pi over 2 to go in one continuous motion. Let's look at another example. In example 2, we want to find the area of the shaded region in the rows, which is 1 petal, given by the equation r equals cosine of 2 theta. Remember that cosine tends to hit right on what would be the x and y axes, where the sine of a rose is tilted off of the axes. Also, because the argument to the trig function has an even coefficient, I'll get double that number of petals. 2 times 2 gives me the 4 petals you see here in the picture. We need to be able to produce this by figuring out how we can trace from one spot to another using just that part. We need alpha and beta, in other words. Now notice that when this is drawn, it's continually hitting the pole here in the center. We have no idea what the angle might be, but we know that r will be 0. Let's start this time with the algebra and the trigonometry to see if we can narrow it down a little bit. This means that what we're trying to compute is where the radius is 0. This means that the cosine of 2 theta must equal 0. Remember from trigonometry that the cosine is 0 at pi multiples of pi over 2. In other words, we need the angle 2 theta to be some multiple of pi over 2 or 3 pi over 2. Since pi over 2 and 3 pi over 2 are pi apart, we could add onto pi over 2 any pi multiple where n is considered to be an integer, positive or negative. Now I need to solve for theta. To solve for theta, we'll be dividing every term by 2. It might help to get a common denominator before you do that, or you may prefer to do it the other way. I like to get the common denominator first so that I can instead then simply do it one time. This will let me write this as pi plus 2 pi n all divided by 2. This is still equal to 2 theta. Dividing by 2 is of course the same as multiplying by 1/2. That means that I'm going to end up on the right side now with instead a 4 in the denominator. I'm looking for these angles here. In trigonometry, you may have done this in various ways, but one of the easiest ways to find these is simply to list some n values. If I let n be 0, 1, 2, and 3, and -1 and -2 and -3, perhaps I can find 2 consecutive angles that will hit the pole. If n is 0, then this reduces to pi divided by 4. When n is equal to 1, this would be pi divided by 4 plus 2 pi divided by 4, or this would be 3 pi over 4. When n is 2, 2 times 2 is 4, and I get 5 pi over 4. I can see the pattern starting to develop in that these are all 2 pi over 4 apart. Again, this would work moving backwards as well. If I want to use -1 for the value of n, this would be pi minus 2 pi, or negative pi over 4. Notice it is again 2 pi over 4 away from the next one in line. Moving backwards, this would be -3 pi over 4. Let's go to the graphing calculator now and see how many times we trace out the rows when we go from 0 to 2 pi and determine where it starts and stops. This will help us to pin down where we need to start and stop so that we can generate one petal. We have shown in the picture that it is the petal that is symmetric across the polar axis. However, this is a symmetric graph. It doesn't matter which petal I take, they all have the same area. You simply need to get one petal drawn and no more. Let's take a look now at the graphing calculator. Go to the graphing calculator and enter in cosine of 2 theta. Be sure to move to the far left to make sure that you have the key symbol represented. You do definitely want that. That is the one advantage that the graphing calculator has over Desmos. It graphs it slowly, beginning at the first setting and extending to the end. My last window was set for the last graph, so I need to reset it now to 0 to 2 pi. I'll leave my theta step to be pi divided by 60, ensuring I get enough points but not too many and bog down the calculator. Now when I hit graph, I can see it going. I forgot to tell it to zoom fit, so it is quite possible that what I see produced here is going to come off the screen, as you can see it does at that point. However, it does look like it only traced it once. Let's do zoom fit now so we can get the whole thing on the screen. Remember to hit zoom, then 0, or scroll to find it. It's searching for a better window, but remember that this will not be squared. Notice it started on the polar axis and moved up in a counterclockwise direction. Third and fourth, and now we need to come around and end the last petal. If I want to get that first petal, then I'll be graphing almost at the end of 2 pi. Or I could try to go backwards. Let's take a look one more time at what we had written down for the values of r hitting the pole. Before we do that, though, we will square the screen because it's bugging me staring at it. This will give us a much better representation. We could take any of those petals and compute the area. This is a non-skewed version of what the rose looks like, where all the petals do in fact look to be exactly the same. Now let's look back at what we had written down about the value of r. We said that r could represent any of these numbers here. In order to get one of those numbers, let's see if going from -pi over 4 to pi over 4 will actually graph the petal that we're looking for, this one here. I know when it started at 0, it started here and began this way. That means that the first one and the first time it hit the pole, it should have been pi over 4. If I move backwards, then the first time it hits the pole would be -pi over 4. I think if I graph between these two, I'll get the petal I need. Let's check it out and see. On the window, go to Window now and select to go between -pi over 4 and pi over 4. Do not use the subtraction. Use the negative down next to the decimal point. We want to use -pi divided by 4. That's our first value. For the second value, we want to go to pi divided by 4. Now we're going to go hit graph. There it goes, and I'm getting exactly what I wanted, just the one petal. Now let's go back to the paper and finish computing the area inside that one petal. We found that our suspicion was correct, that what we do in fact need is the definite integral between negative pi over 4 and pi over 4. The formula is 1/2 r squared d theta. We can move the 1/2 to the front, and now we need r squared. R is cosine of 2 theta, so r squared will be the cosine of 2 theta quantity squared d theta. This is going to be another one of those trig substitution problems where you have to replace cosine squared with the double angle formula. Because cosine is normally an even function, symmetric across the y-axis, it will have a plus in the middle. This is going to give me then this following equation. I'm going to have 1 plus the cosine of double what was in there before. However, what was in there before was 2 theta, so when I double it, I should have 4 theta. Normally, this would be divided by 2, but we can go ahead and move that to the outside of the definite integral. That leaves me an integrand of 1 plus cosine of 4 theta with respect to theta. Now I can simplify the integral by rewriting the constant as 1/4, and I can integrate 1 d theta as theta. For the second part, of course, I am going to have to use u substitution. For the u substitution, we will again choose u to be the argument to cosine, here 4 theta. Du becomes 4 d theta, but I don't have a 4, so by solving for d theta, I get du divided by 4. This will give me another factor of 4 on the outside. The first factor of 1/4 is from the 1/4 that was on the outside. The second factor of 1/4 comes from the expression for d theta. Now I am switching my limit of integration values from theta values to u values. I will then mark this by writing theta equals alpha to theta equals beta, so that I remember that these are not u values, but theta values. The integral becomes the cosine of u du. Now to integrate that, the antiderivative would of course be sine. Plugging into the first integral's terms, I need to evaluate the upper limit of integration and the lower limit of integration. Remember that it is always upper minus lower. If the lower is negative, you will have a double negative. Don't count one for the other. A double negative makes that plus, which gives me 2 pi over 4. That will, of course, reduce to pi over 2. For the next term, I have 1/4 times 1/4, which is 1/16. The antiderivative for cosine is sine. That gives me the sine, and I can substitute back the 4 theta in place of u. This needs to be evaluated between negative pi over 4 and pi over 4. Pull the 1/16 out as a constant factor to simplify your arithmetic. In the next term, then, you need to evaluate the sine of 4 times pi over 4 minus the sine of 4 times negative pi over 4. As we saw in the last problem, the 4's will cancel. Don't expect this to always happen. This is sort of a fluke. The sine of pi is 0, and the sine of negative pi is 0. That term drops out, and I end up with 1/4 times 2 pi over 4, which reduces to pi over 2, which gives me for my final answer then pi divided by 8. That would be the area of one petal. How much area then do you have in all 4 petals? If one petal is pi over 8, then all 4 would be 4 times that, or 3 more of those. That would give me 4 pi over 8, or pi over 2. Let's take a look at another example now. In example 3, we need to find the area outside the cardioid given by the equation r equals 2 minus 2 cosine theta, but inside the circle given by r equal 4. In other words, we want to find the shaded region that you see here. This is a far more difficult problem in that I have 2 conic sections that have been drawn here. One is the circle, which is here, and one is the cardioid, which is graphed inside of that circle. I need the area inside the circle, but outside the cardioid. One way to do this, of course, simply, would be to find the area of the circle and subtract from it the area of the cardioid. And that's exactly the tack we're going to take here. To find this, we need to find the area of the circle. Well, the circle is given by the equation r equal 4, which means the radius of the circle is 4. Since the radius is 4, then I can find the area of the circle by simply writing it. This will give me, and I don't know why it keeps doing that, this gives me instead that the area of the circle, which is given by pi r squared, is 16 pi. Now I need to find the area of the cardioid and subtract that from it. If I can do that, then I'll have the shaded pink area that you see in the picture. To do that, I need to find the area inside the cardioid, which means I need to know, for example, how long it takes to draw this cardioid and what the angles are to take it around precisely once. Probably it's going to be from 0 to 2 pi. Let's go to the graphing calculator and check it out. To save time, I've already put the equation in, and I have readjusted the window to go from 0 to 2 pi, again using pi divided by 60. I've already zoomed fit, so I know I've got the right window, but I haven't zoom squared it to make sure the proportions are correct. So let me do that now. Here's the cardioid, and you can see that it's drawing at one time. To be absolutely sure, go back to y equals, move your cursor until it's on top of the dotted line, and enter twice to get the key shape, the -0. Graph it again, and notice where it starts, at the pole, moving around in a counterclockwise direction. Having it use this option will slow it down a little bit and give you a chance to look at it so you can be sure it's graphing what you want. It comes back to the pole and it stops. That is giving me exactly 1 rotation of the cardioid, which is what I want and need. That means that I can find the area by then coming here and calculating the definite integral for the cardioid going between 0 and 2 pi. The formula is 1/2 r squared d theta. This gives me 2 minus 2 cosine theta in parentheses squared with respect to theta. Be sure that when you square this binomial type object that you do not forget about the product of the outside and inside, which will double each other. Take a moment to complete the definite integral, then turn the video back on to see if your answer matches mine. You may want to pause the video if you need more time to compare your result with mine. Again, notice that I had to use a double angle substitution to replace the cosine squared with 1 plus cosine 2 theta divided by 2. When I was done with the integration, I ended up with a value of 6 pi. Now remember that we are trying to find the area that is outside the cardioid but inside the circle. We found that the area inside the cardioid was 6 pi. That is not my answer. My answer is the difference between the area of the circle and the area of the cardioid. The area I'm looking for of the pink region is 16 pi minus 6 pi, which means that my final area of the pink is going to be 10 pi. Let's take a look at another example. In example 4, we're given somewhat of a challenge. We are asked to find the area inside a cardioid, which is given by the equation 2 plus 2 cosine theta, but to the right of a line given by r cosine theta equal to 3/2. Notice when you look at this equation, if this confuses you why this is a line, remember that we do have a formula that says x is equal to r cosine theta. So all that really says is x equals 3/2. In other words, this is the vertical line here, x equal 3/2, that you see in purple. We need to find the area inside the cardioid that is nevertheless to the right of that vertical line. How are we going to do that? The vertical line is not along a radial line. That means that we will have to compute instead what is along the radial line. We will have to figure out how to find the point where it intersects the line in each of these two places. I can also exploit the symmetry of this cardioid and only compute perhaps the upper half or the lower half and double that area to find the pink shaded region. Let's find the intersection point now. We need to know where those two curves intersect. They'll intersect at the following point when they're equal to each other. So the intersection points are given by the following. 2 plus 2 cosine of theta must be equal to, well, if this is r, I need this solved for r, which means 3 divided by 2 cosine theta. Let's write that down. You could, of course, rewrite that as 3/2 secant of theta if you prefer. Now let's think about how we can solve it. Again, notice that in order to set them equal, I had to represent each side as r, so I could write r equals r. Now that I have this, probably the easiest thing to do would be to multiply through the entire equation by the only denominator I have other than 1. That's the 2 cosine theta. This will probably give me something that is quadratic in form, though not quadratic at all. If I do that now, what do you get? Let's multiply by the common denominator, the only denominator, 2 cosine theta. This would lead to 2 times 2 cosine squared of theta. That would give me 4 cosine squared of theta. That's from the middle term here multiplied by that. When I distribute across the 2, I will get a 4 cosine of theta. You'll see in a moment why I chose to write it in this order. On the far right, the 2 cosine thetas will cancel and it equals 3. This will give me something that's quadratic in form. I can move the 3 to the left by subtracting it from both sides. I could then think of cosine of theta as a u and think of this as 4u squared plus 4u minus 3. Some students prefer to go ahead and write it in terms of u. I find it easy enough to simply leave cosine in there and factor it. This would give me the product of the following two binomial type objects. Be sure to check your products to make sure that you are getting the middle term. On the outside, I have 6 cosine of theta, and on the inside, minus 2 cosine of theta. That gives me a net of 4 cosine theta. This is the correct representation. Solving each of these separately, I have that the cosine of theta could equal 1/2, or that the cosine of theta could equal negative 3/2. Now, it is not possible for cosine of theta to be outside of negative 1 to 1. I didn't do anything wrong. It simply doesn't work. That solution must be extraneous. That means the cosine of theta must in fact be 1/2. What angles would cause the cosine of theta to be 1/2? Remember that cosine represents the x-coordinate. To find the x-coordinate, then what I would do is I would think about having a tall, skinny triangle. If I had a tall, skinny triangle, the short side would be 1/2 and the long side would be square root of 3/2. Since this is a positive 1/2, it can only be in quadrant 1 or 4. This gives me two possibilities, that theta is pi over 3 or any 2 pi integer multiple of that, or that theta is negative pi over 3 in quadrant 4 plus any integer 2 pi multiple of that. This gives me some options for the angle. Let's see what we think it might be by looking at the graphing calculator. Before we get there, let's make a short list of values that we think will work. We have two different options, so we'll need 2 rows for our n's. I have 0, 1, 2, and -1, -2. If n is 0, this line will give me pi over 3. When n is 1, I could think of this as pi plus, getting a common denominator of 3, 6 pi n all divided by 3. That would add on an additional 6 pi n over 3, which would take my next one to 7 pi over 3. When n is 2, I'd get 12 plus 1, which would give me 13 pi divided by 3. These are 6 pi over 3 apart. That means that this one should probably be -5 pi over 3. When n is -1, I get -6 plus 1, which is in fact -5 pi over 3. On the second possibility, I have that n would be 2 pi n would be added to -pi over 3. That gives me a different row. Let's write this row in black. This row would look like the following. For n equals 0, I would have -pi divided by 3. When n is 1, I would want to add on to it. So I could think of this as 4 pi, oops, not 4, my bad. That would be 6 pi n divided by 3 added on to our -pi over 3. That means that I would be adding on 6, so the next value would be 5 pi over 3. When n is 2, I'd get 12 minus 1 would give me 11 pi over 3. These are also 6 pi over 3 apart, but the beginning place is different. Moving backwards, this previous one would be -7 pi over 3. It's not entirely clear where we should be. Let's take a look back at the graph and see if we can figure it out. It looks like it hits here and then goes around and hits again in the very next place. What possible values could this be? If I went from -pi over 3, perhaps the next one is 5 pi over 3. It's hard to say. Let's go to the graph and see if we can compute it. To save time, I've put the two equations into the graphing calculator. Be very careful when you use Zoom Fit that you don't have both equations highlighted and dark. It will try to fit that vertical line, which of course goes forever. Instead, keep only the first one dark and then hit Zoom Fit, which of course is Zoom 0. This will then go and calculate the best XY axis in order to draw the picture. You'll notice it started on the polar axis, comes around and hits the pole, bounces off the pole into the third quadrant, comes around into the fourth quadrant, and ends up back where it started when it traces from 0 to 2 pi. We can also zoom square this if we want the proportions to be correct. This then would give us the following. If we look at it like this, you can see that it is a better picture of the cardioid, a more appropriate representation of it. How can I then get that vertical line on there? Once I have the cardioid correct, then I can go back to y equals, and I can move over and down, and I can highlight that equal sign and make it dark. Now that I have that, I can hit graph, and it will simply draw the vertical line on the graph that I already have. Now I was trying to figure out what values might cause it to go from one to the other. Let's see if we can compute that now. I know that one of the values ended up being what I have here on the screen, pi over 3 and then 7 pi over 3. I also had a negative pi over 3. Let's try from negative pi over 3 to pi over 3 and see if that window gives us the one we want. To do that, again, go to the window and change your theta min from 0 to negative pi divided by 3. Make sure you use the negative and not the subtraction sign. Then scroll down and set your theta max to be pi divided by 3. Now when we go and hit graph, hopefully we'll see only that part and that it will connect and barely touch the vertical line. Bingo, we've got it. That's what we need. Now let's go back to the graph and see how to use symmetry to make this a little bit easier. We've identified that we want these limits of integration. However, the graph itself is symmetric. I could instead go from 0 to pi over 3 and double the area. That will make my problem easier since the lower limit of integration will be 0 instead of pi over 3, or negative pi over 3. Let's take a look at it now. I'm going to double the area from 0 to pi over 3 and use symmetry. I also have a 1/2 for the formula for the area. Now I need r squared d theta. R is 2 plus 2 cosine of theta. When I work this out, remember that I must square r, and that will give me 3 terms. I won't go through all the details, but I will give you the punchline. You'll notice that what I've done is double the integral from 0 to pi over 3. I multiplied out the binomial, I used a double angle substitution and U substitution to evaluate. Then I had to plug in the upper and lower limits. This gave me a final result of 2 pi plus 9 square roots of 3 divided by 2. We should be in great shape, right? Wrong. We're in big trouble. We forgot that when we're dealing with a polar graph, everything starts at the pole. Let's take a look at the graph and see what we actually computed. We thought, the upper area, just in the pink region. That is not what we computed it. By doubling it, we thought we got just the pink, but we got more than the pink. Let's look at the graph again and see what we got. I've made the picture larger here so that you can see what it would look like. In this value, you'll see that I'm going to add on to it what we have actually added into our area but didn't think about. We added in this whole region here. Why? What was it that we did that caused this blue region to get computed in the area when we thought we were just getting the area in the pink? The problem is because this is a polar graph based on a circle. Remember that when I set up the definite integral, I went from theta equals 0 to theta equals pi over 3. This sweeps out part of the polar graph using those rays as the arms. If I had gone from negative pi over 3 to pi over 3, and I'd taken this entire arm and swept it backwards, do you see that it would have in fact included this blue region? In other words, the blue region got included in the area because that is what the radial line from negative pi over 3 to the radial line at pi over 3 sweeps out as it goes in this direction. Now I need to figure out how to get rid of that blue section. Fortunately, we're in good shape there because it is, after all, just a triangle. Since it is, quote, just a triangle, then if I can figure out the base and the height of the triangle, then I should be able to compute its area. Let's write the formula for the area of a triangle, which of course is 1/2 the base times the height. The height can be seen to extend from the pole along the polar axis. We also should be able to find this intersection point since we know that the angle is pi over 3. If the angle is pi over 3, then how can I find it? If the angle is pi over 3, let's find r. R is a function of theta. Remember that my equation way back at the beginning is 2 plus 2 cosine theta. But I know where it is. It's on that line x equals 3/2. 2 plus 2 cosine of the pi over 3 should tell me what the radius is when I'm at this point. How will that help me? Well, it would give me the length of that side. And if I could compute the length of this side, or perhaps the length of that side, then I could use the area of a triangle. This gives me a radius, since the cosine of pi over 3 is 1/2, of 3. Now that I know that the coordinates of this point here where they intersect in polar coordinates is 3, pi over 3, then I can draw at least that part of the triangle extending out along the polar axis, which of course it goes all the way below as well, down to negative pi over 3, like here. This side is 3 and that's 3. These are right angles, of course. Now I need to be able to compute this side or this side in order to determine the area that's contained within the triangle. However, I already know what it is. Remember from the graph that this vertical line that you see here represents the vertical line where x equals 3/2. It wasn't given to us in that form. Instead, they wrote r cosine of theta equals 3/2, but r cosine theta represents x. That means that this horizontal distance along the base of this triangle from here to here must be 3/2. Since it's a right triangle, I can now compute the area of this part using the Pythagorean theorem, or in this case, just the area of the triangle. I don't really need this other side, so let's not do the Pythagorean theorem. Let's just compute the area of that half of the triangle by taking 1/2, the base is 3/2, and the height, well, maybe we do need the Pythagorean theorem. The problem is the 3 is not the height, it is in fact the hypotenuse. That at right angles here, so like it or not, we're stuck with Pythagorean theorem. Let's go to the side and compute it now. I know that that short leg there, which represents the height, has to be the difference between the hypotenuse squared and the short leg squared. That means that it has to be 9 minus 9/4. Written in terms of force, 9 would be 36/4, and that minus 9/4 would give me 27/4. That, of course, is h squared, but not h. To get h, I need to take the square root. Taking the square root of 27 divided by 4 leads to 3 square roots of 3 divided by 2. In this case, I'm considering the height to be strictly positive. Now I can put that into the formula, and I will be able to finally find the area of half of that triangle. Note, of course, that I am in fact only finding this upper triangle that I have here, now semi-shaded in blue. Let's see what we come up with. The area of that half of the triangle would have 8 in the denominator and 9 times the square root of 3 in the numerator. Since I actually have 2 of the same triangle, I need to double it. So the area of the whole triangle would then be 9 square root of 3 divided by 4. Finally, what can we do to find just the pink shaded region? The value I got here was actually the area swept out by the radial arm along the cardioid, which included both the blue triangle and the pink region. I need to now take that number, which was 2 pi plus 9 square root of 3 divided by 2, and subtract from it the other. I had 2 pi, was it minus, plus 9 square root of 3 divided by 2, and subtract from that the area of just the blue triangle, which is 9 square root of 3 divided by 4. To get a common denominator, I could multiply the first term by 2 over 2, giving me 18 square root of 3 over 4 minus 9 square root of 3 over 4, which would result finally in 2 pi from the front plus 9 square root of 3 divided by 4. That represents the area of just the pink region. That last example was an extremely difficult problem. I don't expect you to get that on your first try or your second, and perhaps not on the third. This is something you'll need to go over more than one time. Follow the notes, read through it, give it some rest. Go through it again, give it some more rest, go for a walk, get your brain on something else, and let your subconscious think about what it's been doing. Let's finish up this video with a simpler example. This is one I have frequently given on exams because I just like it. It has a Riemann sum with an inner loop. We know that that means that the value of a, the constant by itself in the equation, here represented with 1/2, must be less than the constant coefficient of the trig function. Here, the 1, which is not written but is multiplied by cosine of theta. When a is less than b, we know that we will have an inner loop in the Riemann sum. What we want to find is the area inside the Riemann sum, but outside of the inner loop. In order to do that, we will use symmetry again to simplify our process. We'll notice also that it hits the pole more than one time. This is a bit of a bizarre problem. You might wonder how this inner loop is represented and how it can get graphed. This point here and this point here cannot both represent r equals theta. Let's see which one actually is one of these points. When 0 is theta, the cosine will give me 1, and 1 plus 1/2 will give me 3/2. You can see barely reading through here that this is the 1 circle, which means this is in fact that point. Let's put the coordinates of that point on the graph so that we have some reference to go by. Scrolling back down, looking at this point here then, this represents a radius of 3/2 when the angle is 0. How then did they get this spot here? It didn't come from 0, and it won't come from 2 pi or any other multiple of 2 pi. What's the only other angle that could appear along this 180-degree line? You got it, it's got to be pi. But pi should be over here, shouldn't it? Not necessarily. If the radius is negative, it will shoot it out this way. Let's give it a shot. What happens when you take the cosine of pi? You get a -1, and 1/2 minus 1 will give me a -1/2. In other words, this point here on the inner loop represents the point -1/2, pi. The angle is pi, but the radius is negative, So instead of graphing to the left of the pole, it shot out the 180-degree line and formed the inner loop. This means that as I come around from 0, how do I get back to the pole? Be aware that the problem with going from 0 to the first time it hits the pole is that it does in fact work like the windshield wipers on your car when it's clearing snow. It's going to clear everything in its path as it sweeps around. That includes this hollowed out loop in the center. We'll have to go from 0 around to when it reaches the pole, and then we'll want to go back in and subtract out this part. That will give us the area of the pink region in the upper half, which we can then double to get the area of the whole thing. Let's start by considering, when does the graph reach the pole? In other words, where does it cross itself here where the radius is 0? Let's look back at the equation to figure that out. We need to know when it hits the pole. That's when r is 0, which that would imply that the cosine of theta plus a half is 0, or cosine of theta equals negative 1/2. When cosine gets 1/2, it is a multiple of pi over 3, the tall, narrow triangle. Because it's negative, that would mean it would be in quadrants 2 or 3 on the unit circle. That would give me reference angles of pi over 3, but in quadrants 2 and 3, that becomes 2 pi over 3 and 4 pi over 3. And of course, we can use any 2 pi multiple of those two values. When then do you think we might be getting there the very first time? Probably at 2 pi over 3. When do we get there the second time? We'll see in a moment on the graphing calculator, but probably it will start here, move around, hit the pole the first time at an angle of 2 pi over 3. Can you see that that angle there does look like 2 pi over 3? Then it comes around the inner loop, comes back around, and hits the pole again, but this time at an angle of, yes, it does look like 4 pi over 3. Then it continues and will return to where it began on the polar axis. Let's take the graphing calculator and see if that is the point we need. You can see that I've already entered in the equation here. Notice I used 0.5 instead of 1/2. Not that it really matters. Don't forget to move the cursor over, make sure you're on the right row, and to change that dotted line into the old-fashioned key symbol to watch it graph. I'm not sure where my window is, so let's check and be sure. Oops, definitely not what I want. I want to see if it graphs the correct Riemann Sum, so I'll first go from 0 to 2 pi to make sure that it is only graphing it one time. I'm leaving my theta step alone pretty much all the time. I rarely ever change it when I'm in polar mode. It almost always stays on pi divided by 60. Remember to zoom fit so you can get the right window, the best X window and Y window for that particular graph. It won't, however, be proportional, and that is because Texas Instruments, stubborn company that they are, insisted on using rectangular screens for decades. And no, I'm not exaggerating. In spite of thousands and thousands of math professors across the United States complaining, they continued to do it till they finally came out with a TI Inspire, which finally had a square window. Hit Zoom Square, option number 5, to make it have the right proportions for what it should actually look like when the X distance and Y distance are the same. Now you can see that it is only in fact graphing the Riemann Sum one time. Let's look back at the work we did to find when it hits the pole. We found that it should be hitting the pole at 2 pi over 3 and any 2 pi multiple, and 4 pi over 3 and any 2 pi multiple. Let's graph from 0 around to 2 pi over 3 and see if it does give us the arc as it comes around this way and stops at the pole. Let's do that now. Go back to your window on the graphing calculator. Leave theta minimum at 0, but change theta maximum to 2 pi divided by 3. Now hit graph again. You don't need to zoom fit it and you don't need to zoom square it because it's already been done. Boom, that is exactly what I wanted. The problem is that on a polar graph, it treats it like a windshield wiper. It's going to clear the whole thing all the way around. That's going to include that loop, which I don't want. Let's now go back to the paper and show what we have so far. Let me sketch for you very quickly what it's going to look like. What we've got is the graph coming around and stopping at the pole. What I mean is that what it's going to do is it's going to treat this part of the polar axis here like a windshield wiper blade, and it's going to sweep out all this region around to here. That means that this will be the region that gets colored in. It will be all of this, which of course includes that loop. That's a problem. It won't be too much of a problem, since we'll then go back and compute the area in half of the loop and simply subtract it from it. The problem is I didn't want this area that was here inside the loop, but it is going to include it. A windshield wiper blade is straight and it does not bend like this, and it's going to sweep out the whole thing like it's throwing off the snow from your windshield. Let's set up the integral that gives us the pink shaded region before we go back to find the area of that half loop. What would we need to use? This should be the integral starting at 0 and going to 2 pi over 3 of 1/2 r squared d theta. This would be 1/2 plus cosine of theta, quantity squared d theta. Take a moment and pause the video to compute what you get, then turn the video back on to see if your integration agrees with mine. I'm not going to go over the nitty-gritty of all of this integration, but let's take a moment and just make sure that you got what I got. Be very careful with your algebra and arithmetic, as it can take a long time to troubleshoot. If you scroll down slowly, and again, you may want to keep your finger near the pause button in case I go too fast, you should eventually arrive at the value of pi over 4 plus 3 square root of 3 divided by 16. Keep in mind, of course, that this is simply the area of the upper part, including half of that inner loop. To take out the inner loop, then, we need to know when it reaches the pole. We know it reaches the pole the first time at 2 pi over 3 and the second time at 4 pi over 3. We know that this point halfway across is pi, so we can integrate from pi to 4 pi over 3 to get the upper half, or 2 pi over 3 to pi to get the lower half. Since it's symmetric, it doesn't matter which half you compute. If you scroll down now, you'll see that I've done that work for you below here. I chose to do the upper half of the loop since that was in fact the one we wanted to carve out. Not that it matters since they're exactly the same. Because we've already computed this binomial type thing squared, I can skip directly to the antiderivatives but plug in the new limits of integration. When I do that, I eventually will find that the area of that half loop is pi divided by 8 minus 3 square root of 3 divided by 16. This, of course, gives me the area I need to carve out. Now, to get the upper half, I need to take the area I found for the whole part and carve out half the loop. By subtracting the area of the half loop from the first part, I end up with pi over 8 plus 3 square root of 3 over 8. But wait, we're not done. This is not the final answer. We need the area for what is contained inside the cardioid, but not, or rather the Riemann Sum, but not inside the inner loop. That final area that does not include the loop is going to be double what we've got, since when we originally computed this, we were only looking at the upper half. We need to compute and double it so that we can get the area of both parts of the graph. In this case, it simply means let's multiply this by 2. That gives me a final area of pi divided by 4 plus 3 square root of 3, also divided by 4. This is another somewhat complicated problem, but I hope that you've enjoyed learning about finding the area contained within a polar graph and learned about how to use a graphing calculator to assist you in doing this. This is the end of this video. In the next video, we'll be talking about finding the arc length for a polar curve and also how to compute the derivative in the polar coordinate system. We'll then use this to find the equation of tangent lines to polar curves at particular points.